this video for Chapter 4 of Basic Sentential Logic and Formal Fallacies and Cognitive Biases. In this video, I'll be talking about material from Section 4.7 of the text, and the topic is using the proof method to derive tautologies, or that's one way of putting it. Another would be to demonstrate that a statement is a tautology. So remember what tautologies are. They're statements, this is from Chapter 2, these are statements that are always true, they can't be false, and in Chapter 2 we developed a method using truth tables to determine whether a statement is a tautology or not. The proof method, on the other hand, is a method for demonstrating validity, for demonstrating that if some given set of statements, call them premises, is true, then some other statement, the conclusion has to be true. Given this, is there any way we could use the proof method to show that a statement is a tautology? Of course there is. That's why I'm doing this video. But how? Well, suppose there's a statement that can be derived from no premises. Okay? What does that mean? We'll talk about what it means, but it's basically what we've got now, where we've been doing proofs. Just suppose we had a proof where the number of premises was 0 instead of 1, 2, or 3, it was 0. If you could derive a statement from no premises, then we could derive that statement from any set of premises, right? You just do this exact same steps you used when there were 0 premises, but not cite any of the premises you had, right? So if you can derive it from none, you can derive it from any of them. Okay? That means that any argument that had that statement as its conclusion would be valid. So you could take any set of premises you want, and if that, the statement we're looking at, is its conclusion, that argument would be valid if you can derive it from no premises. Well, there's only one type of statement that has that feature. And that's a tautology. So if you go back to our Chapter 2 definitions, any argument that has any argument that has a tautology as its conclusion will be valid. Okay? So this is the idea. If we can derive a statement from 0 premises, then we know that any argument that has that statement as its conclusion will be valid. And the only type of statement for which that's true would be a tautology. So the statement has to be a tautology. There's other ways to think about it as well, but this is one way to think about what we're doing and why what we're doing is a way of demonstrating that a statement is a tautology. So here's an example. By the way, this can look kind of scary at first, but think of it this way. This is the last topic of Chapter 4. And in a sense, it's really not a new topic because we're not doing anything different. We're just doing proofs. There's no new rules. There's no new subproofs. We're using conditional proof, indirect proof, and all of the inference and replacement rules we already have to do a proof. So there's really nothing new. The only difference is that now we're adding proofs where we don't start off with any premises. So far, we've always started off with at least one premise. And now we're just going to drop that requirement. And when we drop that requirement, we end up with the proof we're going to do looks something like this. We just have the slash, the therefore, and the conclusion. Okay? All of the ones we've been doing up till now would have some premises listed here in addition to this conclusion, but now we don't have any premises. All we have is the conclusion. What that means is that we're going to have to start off. So this is the only even mildly substantive difference between deriving tautologies and proofs like we've been doing so far, is that you're going to have to start with a subproof, either an indirect proof or a conditional proof subproof. And that's because we don't have any premises to begin with, and all of the inference and replacement rules are things that we apply to a line we already have, one or more lines we already have. And we're not starting off with any lines. We're not starting off with any premises. So the only option left is to start off with a subproof of some sort. But that's not a huge difference because we've been doing subproofs anyway. So let's get moving. Here's a proof. We're trying to derive this conclusion. And other than the fact that there's no premises, it's like any other proof. This is a conditional. I'm going to try I'm going to try conditional proof. Assume the antecedent, see if I can derive the consequent. So I'm going to start off line 1 with a conditional proof subproof. The antecedent I want is not P. So I'm going to indent assume not P, assumption for conditional proof. My goal now is to derive this consequent, if P then not P. Okay. How can I do that? Well, it's going to be pretty straightforward. I've got not P. I can use DI to get not P or not P. I do conditional exchange on that, and I have if P then not P. So now I've managed to derive the consequent of the antecedent that I want, so I can close my conditional proof. Next line has to be a conditional whose antecedent is my ACP, consequent is my last line. If not P, then if P, then not P. Justification is 1 through 3 conditional proof. So you should be able to see this is exactly like what we've been doing. The only difference is that we're starting off with 0 premises. As a result, we're going to have to start off with some kind of subproof. But aside from that, it's just like any other proof. The only thing I want to just alert people to is that some students are so used to there being premises up here that they can apply rules to, that when there aren't any premises and the only thing that's up here to begin with is the conclusion, they try to apply rules to the conclusion. Obviously, don't do that. This is just the conclusion. It's telling you what it is you're trying to derive. It's not something you can use rules on, but it's telling you what your target is, what you're trying to eventually get. Okay, let's do a different proof. I'm going to do this one in a couple of ways. This is a tautology, and it's a disjunction. And remember, anytime you're trying to derive a disjunction, you can use conditional proof as long as the conditional you derive, the antecedent is the negation of the first disjunct. And we went through this in chapter 3 a lot. But I'm going to use conditional proof to eventually get this disjunction. If you don't remember from chapter 3 the connection, just wait until the end and you'll be reminded of it. So I'm going to assume this, not if G then H, basically the negation of the first disjunct here. If this was just a conditional, if this was just a horseshoe, I would just assume the antecedent. But you'll see when we get to the end why I'm assuming this. But now my goal is just going to be to derive this statement here. If not G, then J. How am I going to do that? Well, there's a couple of ways I could do it. This is itself a conditional. I could do an embedded conditional proof, assume not G, derive J. I could do an indirect proof, assume the negation of this. Or I could just use inference and replacement rules. That's the way I'm going to do it. This is a negated conditional. I can't really work with that, but I can work with a negated disjunction. So conditional exchange and then De Morgan's gives me G and not H. I'm going to simplify the G off, and you'll see why. I'm trying to derive this. If I can disjoin J on here by DI and then do conditional exchange on this, I have not G then J, which is this. So I've derived the thing I want. Now, if chapter 3 was a long time ago and you don't remember the connection between conditionals and disjunctions, this might be puzzling you. But just wait. I'm going to go ahead and close this off now. And then I will get, this is a conditional proof. So it's going to be a conditional that has this antecedent and that consequent right here. Okay? Now I'm not done because this is not that, obviously. But I knew that if I could get this conditional that had this antecedent, which was the same as that antecedent, where the consequent was the negation of this disjunct, then when I do conditional exchange on this, horseshoe becomes a wedge. I negate the first component. Now this does become this disjunction. Okay? So it's because I realized that if this is my last step, this could be my second to last step. And then that because this was a conditional, I could use this conditional proof where this was my ACP, and then I would end with this. That's why I came up with this strategy for this proof. Now, suppose you thought of a different way you might try to do this proof. So same proof, same statement here that we're trying to derive. And you might think of it this way. You might think, well, this is going to be my last step. How could I get this last step? By the way, I got this last step by deriving this conditional and then doing conditional exchange on it. But that's not the only way you might be able to do this. You might look at this and think, this is a disjunction. So if I could just get this first disjunct here, something like this, I could use DI to get the whole thing, right? And the justification would just be whatever line number this is, DI. And so now the question is, can I get if G then H? And you might think, well, that's a conditional. I could use conditional proof, assume G, derive H. Once I've assumed G, how could I get H? Maybe I can do an indirect proof here. Assume H, derive an explicit contradiction, or assume not H. That gives me H, G then H. Here's the issue. And let's just back up to this. Everything I've just said so far, that won't work. And the reason it won't work is this. This is my last line. The strategy was to say, well, if I can derive this, I could just disjoin that. In principle, that's correct. If you could derive this, you can do DI to get that. That's fine. Problem is, you're never going to be able to derive this. Because remember, we don't have any premises. The only way we would be able to derive this from no premises is if this is a tautology. Okay? Now, we know this is a tautology because I gave it to you as a proof, and unless I screw up and make a typo, I'm not going to give you as a tautology proof a statement that's not really a tautology. So you can trust that this thing really is a tautology. But that doesn't mean that either disjunct by itself is a tautology. Okay? And this one isn't. If you do a truth table for this, you'll see that if G then H isn't a tautology. So there shouldn't be any way you can derive this from no premises. So all of this planning here, you could try it this way, or you could try assume G, derive H. You'll never be able to do it unless you make a mistake somewhere, for the simple reason that this is not a tautology. Okay. What that means is that, and also this other disjunct is not a tautology either. You can do a truth table for that to see. The whole disjunction is, do a truth table for the whole disjunction, you'll see the whole disjunction is a tautology, but neither disjunct by itself is. There is another way to do it though, and I'm going to do this in a kind of funky way. I've said a number of times that there's an infinite number of ways to correctly do any proof. So here's a way of doing this that is a little bit funky, but once I've done it, I'm going to walk through the thought process behind how you might have gotten there, and you'll see how I got there. Same tautology. I'm going to assume G, assumption for conditional proof. Why? We'll get to that. Line 2, I'm going to use conjunction on what two lines? Line 1 and line 1. So I'm just going to get the conjunction G and G. Yeah, I applied a rule to the same line twice, but that's okay. We haven't done that so far, but there's nothing that rules that out. And it's truth preserving. You can see that you don't all of a sudden get a non-truth preserving rule if you do this. And then I'm going to simplify one of these conjuncts off to just get G again, close this subproof, and I get if G then G. Now this looks weird, and the whole reason I did this conjunction and then simplification was just I wanted G here. In some systems of logic, they include a rule called reiteration or repetition that just lets you repeat a line. That would have saved us a step if we had that rule. We don't have it, but we can still do the same work by just doing this anytime we want to reiterate or repeat. The reason I went through all this is I just wanted this conditional, which is a tautology, and you'll see why I wanted that in a minute. Also, there's a slightly more elegant way I might have done this, just to show you this before I continue with the proof. I might have assumed G, ACP, just like I did here on line 1, and then said, oh, what's my goal now? My goal is just to end my subproof whenever I get to the consequent I want, which is G. Oh, I've got that here, so I'll just close the subproof now, close it on the same line I opened it, and then get if G then G, and that's by lines 1 through 1 conditional proof. That'd be a little more elegant, but this is fine. No mistakes were made. I've got if G then G. Now I'm going to do conditional exchange to get not G or G. Now I'm going to do DI. So this is this first statement, and then I'm going to disjoin H or J. I can use DI to disjoin anything. I'm going to get H or J. And now what I'm going to do is I'm going to use a lot of commutation and association to move these disjuncts around and change their groupings. And you'll see where I'm going to end up with this. But basically I want to move the H over here, and I want to get the G over there where the H is. Okay. First thing I'm going to do is association on line 6. Now you might look at this and go, whoa, 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 what happened here? How did I get this? Because you might think of association, here's the rule, as applying when you've got 3 disjuncts and we've got 4 here. Well, we also have 3. Think of it this way. That's a disjunct, that's a disjunct, that's a disjunct. And up here, the H is associated with the J. It's the first disjunct in this disjunction, where J is the second disjunct. I'm going to change it so that this H is associated with the magenta disjunct here. So one way to think of it is I've moved this parenthesis past the J, past this wedge, and moved this parenthesis past the magenta one. Okay, so anyway, I've associated the H with this instead of with the J. Now I'm going to do another association here, only I'm only going to work on these 3. And this G, instead of associating it with not G, I'm going to associate it with the H. So I'm going to move these parentheses over 1, so that I've got G or H here in the middle. Now I'm just going to swap the order of the H and the G. H over here, G over there. And now I'm going to go backwards to move these parentheses and brackets back where they were. So I'm going to move these brackets over so that not G and H are associated, and then move these brackets over to the right so that the G and the J are associated. This G is no longer associated with that, but it's associated with the J. What is this all about? Well, you can see why. If you look back up here, if I just do conditional exchange on these 2 disjunctions, so I'll do it on this one first. Disjunction becomes a conditional, negate first component. Now I'll do it on the first one. Wedge becomes a horseshoe, negate first component. Now I'm done. This is that statement. Okay? Now, you might look at this and go, whoa, that's kind of crazy. How would anyone think of this? That doesn't seem, Here's how you might think of it. I'm trying to derive this, which means this is going to be my last line here. Somehow I've got to end up with this. Now, I've done enough conditional exchanges to know that this disjunction, each of the disjuncts is a conditional, but these are also, each one of these is one step away from a disjunction. Okay, so my second to last line could just be this, where essentially I've got 4 disjuncts here. Okay, and I know if I can get this in 2 steps, I can get my conclusion. How can I get these disjuncts? Okay, these 4 disjuncts. And now what I'm thinking is that, yeah, they're grouped and they're ordered in a certain kind of way, but I'm familiar enough with association and commutation that I know that if I can just get these 4 statements put together as disjuncts, doesn't matter how they're grouped, it doesn't matter what order they're in, I'll be able to get them in this grouping, in this order, eventually, with association and commutation. So now I'm just thinking of these 4 disjuncts. Somehow I need to get these. Okay, how could I do that? Well, if any part of this is a tautology, I can derive that part and then just disjoin the rest with di, right? So for example, if not G was a tautology, it's not, but if it was, if I could somehow derive this from no premises, then I could just disjoin the other disjuncts here and then do my association commutation to get this. So what I'm thinking is, this particular way won't work because this isn't a tautology, but is there some part of this that is? Okay, not G isn't, okay, no. What about H? H isn't a tautology. Obviously, it's an atomic statement. They're all contingencies. What about not G or H, right? What about these first 2 disjuncts? Is that a tautology? No. Do a truth table, you'll see it's not. What about the first and the third disjunct? Not G or G. Yes, that is a tautology. Remember, any statement disjoined to its own negation, that's going to be true no matter what. So now I know that if I can just derive this tautology, I could then disjoin the other 2 disjuncts to it and then associate and commute until I've got them in the right order. And you'll see that's exactly what I did. I got this tautology, not G or G. I then disjoined the other 2 disjuncts. These were the 4 disjuncts. And then I just did association and commutation to get them in this order. And then once I had them in this order, conditional exchange to end up there. I've said a bunch of times that there's an infinite number of ways to correctly do any proof. And this is just an example of that. There's a bunch of ways to do this proof, including ways that you might not think of. One thing this means is that even though there's a huge number of proofs to do for exercise, you can always go back and do them again. So just because you've done a proof once and done it correctly doesn't mean that you're all done with the exercises. You can just go back and say, yeah, I've already done these 5 proofs. I'm going to do all 5 of them, but in a different way than the way I did them the first time. And sometimes that can actually be more challenging. With the easy proofs, maybe you did them in a certain way. Trying to do them in a different way, you can do them, but it might take you a few more steps. It may not be as easy. Okay. That's just to say that you should never run out of potential practice. Okay, that's it for this video. Keep practicing and good luck.